Hello everyone. Now we will quickly discuss about moment area theorems. Moment area theorems are used to find out the slopes and deflections in a beam, but the moment area theorems will not give you the slopes and deflections directly. They will give you the change in the slopes between 2 points, and they will give you the deviation of a specific point of the beam with respect to a tangent drawn from another point. Now we'll quickly go through the statements, moment area theorem statements, and then see how we can apply them. So the moment area theorem 1 states that the change in the slope between any 2 points on the elastic curve will be equal to the area of M by EA diagram between these 2 points. So the first thing here is, here M by EA diagram means the bending moment diagram divided by flexural rigidity EI. E is the Young's modulus, I is the moment of area. For all the problems that we will do in this course, EI is a constant. So if you know the bending moment diagram, you pretty much know the M by EI diagram. You just have to divide the ordinates of bending moment diagram with the value of EI. That's it. Now we have to look at the nomenclature of the moment area theorem number 1 before we proceed to the problem. For example, if I have this specific simply supported beam, if I choose 2 points A and B, if I draw a tangent through point A, that is referred to as tan A. The blue line here is referred to as tan A. The green line that passes through point B is the tangent B. The angle made by the tangent B with respect to the tangent A is referred to as theta B by A. Here the point of interest is B. That means you are trying to measure the angle made by the tangent that is passing through B with respect to the tangent that is passing through A. So what does this statement say? This statement says that if you want to know the value of theta B by A, you just have to evaluate the area of M by A diagram between A and B. That is how you get theta B by A. Please remember that this theta B by A is not theta B. What is theta B? Theta B is the slope of the elastic curve at the point B. How do you get that? You get that by evaluating the angle made by this tangent with the x-axis or the undeflected beam, which in this case is simply supported beam. So the sign convention that we will use here is, our theta B by A is anti-clockwise if M by A diagram area is positive. Our theta B by A is clockwise if the M by A diagram area between the points A and B is negative. So whatever angle you might get, the units for the angle is radians and not degrees. Please remember that. So although I haven't taught you how to evaluate the theta B here, it is important to note that we will somehow use this information in order to evaluate the slope at point A or point B. So moment area theorem number 2 is a theorem that will help us find out the deflections. But the most important thing is the moment area theorem number 2 doesn't give you the deflections directly. Instead, it gives the vertical deviation, not deflection, of the tangent at a point A on the elastic curve with respect to the tangent extended from another point B, and that is evaluated by taking the moment of the area under the M by A diagram between the 2 points A and B. I know that this might sound like Greek and Latin, so let's look at the diagram here. For example, if this is the beam with the arbitrary load, and if point A and point B are chosen, if this is the M by A diagram, then here T B by A is nothing but the deviation of the point B measured with respect to the tangent that is passing through A. Here tan T A by B is nothing but the deviation of the point A measured with respect to the tangent that is passing through B. So the most important thing is this subscript B denotes the point of interest. That means if you are looking at the point B and trying to evaluate what is the deviation of this point B, that will be the point of interest and that should appear first. So here the point of interest is A because you are trying to see the deviation of the point A with respect to the tangent that is passing through B. So for example, if I want to evaluate this dB by A using moment area theorem number 2, what I have to do is I just have to simply evaluate the area between the points A and B in the M by EI diagram. So evaluate the area and then multiply it with the distance from the point A, distance of the centroid of this area from the point A, which in this case is x bar, if I want to find out TA by B. So for example, if I want to find TA by B, I have to multiply the M by EI diagram, area of the M by EI diagram between the points A and B with x bar, where x bar is the distance of the centroid of this M by EI diagram from the point A. So whatever is the point of interest, the moment of area should be always evaluated with respect to that particular point. For example, if I want this dB by A, I have to once again evaluate the M by A diagram enclosed by these 2 points A and B, and then have to multiply that area with the distance from the centroid of this M by A diagram to the point B. So once again, as I previously mentioned, both moment area theorem number 1 and moment area theorem number 2 will not give you the slopes and deflections directly. They only give you change in the slope and deviation of a specific point with respect to a tangent drawn through another point. So we have to somehow use either intuition or trigonometry in order to evaluate the slopes and deflections. Now we'll look at multiple examples, but before that we'll also look at the sign convention in the case of moment area theorem number 2. The sign convention is, if somehow your moment of area is positive, then the point of interest is above the tangent from which it was measured from which the deviation is measured from. Once again, if the moment of area is positive, that means your point of interest is above the tangent that you used in order to measure the deviation. Similarly, if the moment of area is negative, that means your point of interest lies below the tangent from which you measured the deviation. So now let's quickly go through some sample problems that will help you understand the moment area theorems in a better way. So the most important thing is we just simply have 2 types of problems in moment area theorems. Problem set number 1, where at least the deflection and slope at least one point in the beam is known. And the problem set number 2, you do not know the slopes and deflections at any point in the beam. So here, this one belongs to the set 1, where you know the deflections and slopes at this particular point. So you can exploit that and easily evaluate the slopes and deflections. So here you have a cantilever beam and you have a 2 kip load acting at the free end, and you have to find out the slope at the point B. So whenever you want to find a slope at the point B, the very first step is draw the elastic curve. So you will draw a qualitative elastic curve, and at the point B you will draw a tangent. So now I have to draw another tangent so that I can find out my theta B. What is theta B? Theta B is nothing but the angle made by this tangent with respect to the x-axis. As this is the fixed end, I pretty much know that if I can draw a tangent at the point A, it will pass through the x-axis or it will coincide with the undeflected beam AC. And the good thing is, the angle made by this particular tangent with this undeflected beam AC, which is nothing but the tangent that is drawn through the point A, is nothing but theta B by A, but the theta B by A is also our theta B, which is our slope. So So it turns out that our theta b by a is exactly same as that of theta b. That means the angle made by the tangent that is passing through point B with the tangent that is passing through A is nothing but the slope of the beam, because the tangent A coincides with the x-axis or the undeflected beam. So if this is the case, how do I evaluate this b by a, theta b by a? Whenever I want to evaluate theta b by a, I just have to go to moment area theorem number 1, and I have to look at these subscripts and evaluate the m by ei area between these 2 points, and that is what I will do next. So here is the beam that is given to us. I have to have the bending moment diagram for this beam. Just because this is a cantilever and this is the load sitting on the free end, my bending moment diagram will be a triangular diagram, and in this diagram I just have to evaluate the area between the points A and B to get theta b by a, which is nothing but my theta b. So I just have to evaluate the m by e diagram area between these 2 points, which I get, and whatever I get will be the slope at the point B in radians. So here the trick is, so you should always draw the tangent through the point of interest. You should always draw the tangent at another point so that you will be able to find out what is asked in the question. For example, here you were asked to find out the slope at the point B. In this case, if I draw a tangent through point A, just because it coincides with the x-axis, my theta b by a will become equal to theta b. But this kind of scenario may not exist all the time. So we'll look at this category 1 or type 1 kind of problems, and we'll also look at type 2 kind of problems where we do not know beforehand the angles or displacements at specific points in the beam. Now let's look at example 2. Here once again I have a cantilever beam. Here I am asked to find out the deflections at the point B and C. This is exactly same as it of what we have seen in the previous problem, with a single difference that the moment of areas of the span AB is different from moment of area of the span BC. I have a concentrated moment of 500 Newton meter acting on the extreme end C. So the very first step is always to draw the elastic curve. If I draw an elastic curve, here the elastic curve is drawn in red color. Please remember that the slope and deflection at this particular point is 0. So just because I am asked to find out the deflections at both points B and C, I have to draw tangents at B and C. And the most important thing is, if I draw a tangent through this particular point that coincides with the undeflected beam, which is nothing but ABC. So not only that, the deviation of the point B with respect to tangent that is passing through this point is nothing but my delta B, right? So the deviation of the point B with respect to the tangent that is passing through point A will be my delta B. Similarly, the deviation of the point C with respect to the tangent that is passing through point A will be my delta C. Tc by A is equal to delta C and delta B is equal to Tb by A. So once I know this one, all that I have to do is I have to find out what Tc by A is and Tb by A is. To do that, I have to know the M by E diagram for this beam. This being a cantilever beam, drawing M by E diagram is pretty easy. So this is what I have. But please remember that whenever this will be a rectangular box, but just because my EI values are different for both the beams, one beam will have higher M by EI and the other beam will have lower M by EI. Now I have to find out Tb by A. So how do I find out Tb by A? I have to evaluate the M by E area between the points B and A and take its moment from the point B. Okay, B is the point of interest. So I evaluated the M by E area between the 2 points A and B, and then multiplied with 2 meters because there is a distance between the point B and the centroid of M by E area. When it comes to evaluating T C by A, I have to evaluate 2 areas. I have 2 rectangular portions. I have to evaluate 2 areas, and the first area is 5 meters away from the point C, and the second area is only 1.5 meters away from the point C. If you want to see that clearly, you can go back and see in this diagram. This area is just 1.5 meters from C, and this area is 5 meters from C. So that is how you get both delta B and delta C. Another important thing is, just because our moment of areas are positive, that means that the deflected curve lies above the tangent A that we have already discussed in the past. So this is the last kind of problem that we can have in set 1, where we could tactically use the boundary conditions or the end conditions or the symmetry conditions so that we can fix the point where we can draw the second tangent. So for example, if we are asked to determine the slope of a point C of in this particular beam, so this particular beam is special. Of course, this is a simply supported beam with a concentrated load sitting at the middle, but the important thing here is this is a symmetric beam. Symmetric beam in the sense the maximum deflection will happen at the point D. So whenever the maximum deflection happens at a particular point, you know that the slope at that point is 0. Maximum deflection corresponds to the point where the slope is 0. So keep that in mind. And when we determine where we have to draw the second tangent, this comes into the play. For example, we were asked to find out what is the slope at the point C. So we have to draw the elastic curve. And just because we are asked to find out the slope at the point C, we have to definitely draw a tangent through C. But where do we draw the second tangent is a question. But we pretty much know that the slope at the point D is 0. So let's draw a tangent through D, and that passes through x-axis or parallel to the undeflected beam, just because the slope at the point D is 0. So the theta D by C, that means the angle made by the tangent D with respect to the tangent that is passing through C is nothing but theta C, because theta C is nothing but angle made by this particular tangent with respect to x-axis. Here in this case, the tangent that is passing through D is parallel to x-axis. So your theta D with respect to C becomes your theta C. So in this particular example, you are able to draw a tangent here only because this is a symmetric beam, and you pretty much know that the maximum deflection occurs at the point D. Don't make any such choices in the final exam, because you may not know where exactly the maximum deflection might occur, unless and until it's a symmetric beam. If it is a symmetric beam and a simply supported beam with load acting at the center, you pretty much know that this is a symmetric beam and you can use this rule. Otherwise, you are not supposed to use this rule. Okay, here theta D by C is equal to theta C. So here what you have to do is you just have to evaluate the M by E area between the points D and C. So from there you need to evaluate the bending moment diagram for this particular beam, which is given by this triangular bending moment diagram is the final bending moment diagram. You just divide it with flexural rigidity EI and you get your M by EI diagram. And finally we have to evaluate the area between the point C and D to find out our theta C, which turns out to be 0.112, and the most important thing is the units are radians and not degrees. Now let's look at some examples where we we can't use the boundary conditions or the symmetry boundary conditions in order to locate the second tangent. For example, this is a beam, simply supported beam, with a load which is definitely not located at the center, so we pretty much do not know where the maximum deflection in this beam occurs. So we have to tactically place our second tangent so that we will be able to find out the slope at a point C on the beam. Okay, this C is definitely not located at the center, and this 8K is not located at the center. This is not a symmetric beam, and you do not know the slope at the point A, you do not know the slope at the point B. So now we have to use the second tangent along with some trigonometry rules to find out the slope at the point C. How can we accomplish that? So it would become much more easy if we know the slope at any point in this beam. For example, if you want to know the slope at the point A, what would you do? You can just simply draw a tangent through point A, and you know that this point B is not going to deflect, so this is TB by A. If you know the bending moment diagram for this beam, you can easily evaluate TB by A. How can you do that? You can just simply evaluate the M by A diagram area between these 2 points and multiply it with the distance of the centroid of this M by A diagram to the point B. So once you know TB by A, you could just simply divide it with the span of the beam to get what is this phi, or the inclination of this tangent that is drawn through point A. And as usual, you should definitely draw a tangent through the point of interest, which is C. And if you draw a tangent through the point C, that is denoted in green here, the angle made by this green line here with respect to the blue line, which is the tangent A, is nothing but theta C by A, right? Now you have theta C by A, and you already know what is this phi, because phi is nothing but TB by A divided by the span of the beam. So the left out angle here, this angle is nothing but your theta C, right? This is the tangent C, and this is the angle that is made by the x-axis, or with the x-axis. So what you have to do is you just have to subtract theta C by A from phi, where phi is nothing but TB by A divided by 24, which is the span of the beam. So here we made use of trigonometry, and we didn't make use of known slopes or deflections. So this is the second type of problem. So once again, the procedure for evaluating this TB by A and theta C by A remains exactly the same. And this one is obtained by taking the first moment of M by A area above the point B, and this is obtained by evaluating the enclosed M by A area between the point C and A. Now let's look at a different problem. So this is another simply supported beam. We are supposed to find out the deflection at the point C. Although this point C is located at the center of the span, please remember that the loading is asymmetric here, so this will not bend symmetrically. So we do not know whether the maximum deflection is at the point C or not. Okay? So from here we have to determine what is the deflection at the point C. Now let's see. If I draw a tangent through point B, the deviation of the point A with respect to this tangent B is nothing but TA by B, and the deviation of the point C with respect to this tangent is called TC by B. But the important thing is we are neither interested in TA by B nor TC by B. We are interested in delta C, which is given by this one. If we magically find out this total distance somehow, if we can magically find out the total distance between these 2 points somehow and subtract this known TC by B, then we get the delta C. How can we do that? In the first place, find TA by B and use similar triangles to find out what is this total length. So how do I find out TA by B? Find out the M by EI area between these 2 points and take the moment of that M by EI area with respect to the point A. Then you will have TA by B. So using similar triangles, we pretty much know that this whole length is nothing but TA by B divided by 2. So if we subtract TC by B from TA by B by 2, you will get delta C. That is what was done. Next, so we will have T. You have to find out what is TA by B divided by 2 and subtract TC by B from that. So in the next example, which is this overhanging beam, we have to find out what is the value of delta C. This also belongs to the second category of problem where you do not know the slopes or deflections at certain points, which will simplify your life. So here the first step is always to draw the elastic curve, which is drawn in the red line here, and the second step is always to put the tangent at the point of interest, which is C here. We drew a tangent at the point C. We are very interested in this delta C, but as I previously mentioned, moment area theorems will not let you evaluate this delta C directly. Instead, what we have to do is we have to draw a tangent through the point A. The deviation of the point B with respect to this tangent A is nothing but TB by A. So we can easily evaluate this TB by A because it's nothing but the moment of M by EI area between these 2 points with respect to the point B that can be easily evaluated. When once you know TB by A, you can use similar triangles to find out what is this value, what is this value here, this value, because we know that this is 8 meters and this is 8 meters. This TB by A will become 2 TB by A at this end. And when once you know this value, you can evaluate TC by A, which is nothing but the deviation of the point C with respect to tangent A, and by subtracting this 2TB by A from this TC by A, you get delta C. That is what is written in the next step. So by subtracting twice TB by A, you get TC by A. So here I have drawn a much more clearer version of the similar triangles. You have your TB by A here, and at the end of the span you will have 2 TB by A. You just have to subtract it from TC by A to get your delta C. So evaluating TC by A and TB by A will be using the moment area theorem number 2, and it is no different from what we have discussed previously. So in a nutshell, we have discussed 2 types of problems for moment area theorems. The very first type of problem is the cantilever type of problem, and a beam in which you have a symmetric deformation. The second type of problems are general problems wherein you do not know where to place your second tangent. In such kind of problems, we have to use trigonometric rules and similar triangles to find out the unknown slopes and deflections. Now let's go to the next concept, which is conjugate beam method. The conjugate beam method is the most simplest method among all the 3 methods that we discussed in the class, and it will have 2 theorems. I'm not going to read these theorems once again, but if you want to find out the slope in the real beam, you have to find out the shear at the same point in the conjugate beam. If you want to find out the displacement in the real beam, you have to find out the bending moment in the conjugate beam at the same point. So now what is the conjugate beam and how do you get the conjugate beam from the real beam? The first and the foremost thing is the length of the conjugate beam is equal to length of the real beam. The second thing is, in order to come up with the conjugate beam, you have 2 rules. The first rule is, if the real beam allows slope, then the conjugate beam should develop shear. If the real beam allows displacement, the conjugate beam must develop a moment. So here we have different real supports and the corresponding supports that you see in the conjugate beam. Okay, a pin will allow rotation, but it will not allow deflection. So the conjugate beam should allow shear, but it should not allow moment. That means a pin will transform into pin. Using the same rule, a roller will transform into roller, and a fixed support will transform into free support. A free support will become fixed support. An internal pin will transform into hinge. An internal roller will transform into hinge. And a hinge will transform into internal roller. You need not by heart the real beam and the conjugate beam supports. I'll give this diagram in the final exam, so don't worry, but just simply try to understand the concept. So the other important thing that you need to remember is, after you translate the real beam into the conjugate beam may sometimes be unstable. That's totally fine. So in this particular example, we have an internal hinge here. If you apply a load here, this segment would just simply fly off, would just simply rotate rigidly, making it unstable. That is totally fine. You can have this kind of thing in your conjugate beam. Don't worry about it. You just have to evaluate the shear force and bending moment, assuming that this is stable. So now what is the procedure? The procedure is something like this. In the first step, you have to draw the conjugate beam for a given real beam. And as I previously mentioned, if the real support allows slope, conjugate beam support must develop shear. And if the real support allows displacement, conjugate beam support must develop moment. You need not by heart anything. I'll give you the chart that I previously showed you in the final exam. So in the step 2, this is important. In the step 2, you have to load the conjugate beam with M/E diagram of the real beam. Don't transfer the loads that you see on the real beam onto the conjugate beam. Instead, you have to transfer the M/E diagram of the real beam onto the conjugate beam. So, and what is the sign convention? If the M/E diagram is positive, that means load should point upwards. If the M/E diagram is negative, then the load should point downwards. And the step 3 is when once the conjugate beam is loaded with the M/E diagram, the point at which you want to know the slope in the real beam, the same point in the corresponding conjugate beam, you have to look for the shear if you want to find out the slope. You have to look for bending moment if you want to find out the displacement. So slope in the real beam is equal to shear in the conjugate beam. The reflection in the real beam is equal to moment in the conjugate beam. Now let's quickly look at a couple of examples to help us understand what is going on. Once again, the sign convention. If the shear in the conjugate beam is positive, that means the slope in the real beam is anti-clockwise. If the moment in the conjugate beam is positive, that means the reflection in the real beam is upwards. So once again, we have a simple example here. We have a cantilever beam, and we were asked to find out the slope and deflection at the point B. So, as I previously mentioned, the very first step is to come up with a conjugate beam. In the case of a cantilever beam, the fixed support will transform into free end, and the free end will transform itself into a fixed support for the obvious reasons which are mentioned here. This will be given in the final exam. So the transformation of the supports will be given in the final exam, so I don't want to discuss any further about it. So the second step is to find out the M/E diagram for the real beam. So this is the real beam. You have to find out the M/E diagram. This is a cantilever beam. So this will be the M/E diagram for this particular beam. Please remember that the M/E diagram is negative. It's not positive. So according to the sign convention that we previously discussed, we should have this loaded up on the conjugate beam in the downward direction because our M/E diagram is negative. So in order to find out the slope at the point B, we have to find out the shear at the point B prime in the conjugate beam using method of sections. In order to find out the deflection at the point B in the real beam, we have to evaluate the bending moment at the point B prime. So once again, whatever theta you might get, that the units will be radians, and whatever delta you get, that will have the units that you used for the rest of your calculations. So one more example. Here we have a simply supported beam with 8 kN load sitting on the span. So we were asked to find out the maximum deflection. We are not asked to find out the deflection at a particular point. So once again, as I previously mentioned, a real simply supported beam will transform itself into a simply supported beam, simply supported conjugate beam. So the first step is pretty easy if a simply supported beam is given to you. The second step is to evaluate the M by E diagram for the real beam, which in this case turns out to be this triangle with an ordinate of 18 by EA, maximum ordinate of 18 by EA. The most important thing is this point C is not at the center, so this is not, this span is not equal to this span. And somehow I assumed that the maximum deflection will happen in the span A prime, C prime, which is nothing but this span. So if the deflection is maximum, that means dV by dx is equal to 0, where V is the deflection. So dV by dx is 0 means slope is equal to 0. When slope is equal to 0, our shear force in the conjugate beam should be equal to 0. So I assumed that the shear force in the beam is 0 at a distance x from this support, and I evaluated the shear force in terms of x and equated it to 0, and I got an x value of 6.71. So 6.71 lies between 0 and 9 meters. And if I got a negative value here, or a value which is greater than 9 meters, that means there doesn't lie a point at which dV by dx is equal to 0 within this span. But I got a good number which lies between 0 and 9. So that itself says that I have a maximum deflection in this particular span. So now that I know that the deflection is maximum at 6.71 meters, what I have to do is, I have to evaluate the bending moment at x is equal to 6.71 in the conjugate beam to find out the maximum deflection in the real beam. That is what I have done here using method of sections, which is pretty easy. After all the calculations, I evaluated the maximum deflection to be minus 16.8 mm in the real beam. So this is double integration method, moment area theorems, and conjugate beam method in a nutshell. If you have any questions, I'll be available in my office on Thursday and also on Wednesday, so please contact me.